Thank you virtually, Richard, for that introduction. My name's Ian Benson. I'm one of the conveners of the Functional Programming and Computer Algebra Group. Thank you for coming to our session today. It takes the form of a report to update ATM on a session that Neil and I gave at our conference in 2022. Our colleague David Vaccaro sends his apologies. He's recently changed schools and he's not able to attend conference this year, but a paper that we wrote based on his work is available for download from the Padlet, and I'll be touching a little bit on the content of that paper at the end of our talk today. We hope to speak for about half an hour, and we will be available to take questions over Zoom if the technology works for the last 15 minutes. This year, David, Neil and I have been exploring functional programming and computer algebra environments with sixth form teachers. We've created several resources for use in the classroom, and we've experimented with designs for teacher professional learning. In this talk, we're going to look at 4 of our resources. 3 of them are taken from ATM archives, and 1 is a resource recently created by David. We've transcoded all the software into Haskell. That's come from BBC Basic, a graphing calculator script, and from Mathematica. Our starting position is what Professor Hyland calls the unambitious syllabus for A-level mathematics and further maths. Martin found that today's curriculum doesn't prepare students who wish to follow an ambitious university maths course. I also believe it's inadequate preparation for functional and object-oriented analysis, which should be the core elements of a modern informatics course. In 1982, Martin Löf, a mathematician and computer scientist, drew attention to the way that programming was becoming an activity akin in rigor and beauty to that of proving mathematical theorems. Programming achieves this because of the similarity between concepts such as program, procedure, and function, data type and set, or type in mathematics, and value of a data type with an element of a set, or in mathematics, an object of a type. We can add to this table of similarities the relationship between computational recursion and mathematical induction, which we're going to talk about a little more today. It's been shown that recursive functions like those found in Haskell and other programming languages provide a way for students to develop an intuition for formal inductive proof. And we'll see some simple examples of these in our teacher professional learning resources. Proof is hard for most students, and the context for inductive proof is proof. However, the context for recursion, which is a kind of proof in action, makes it much more accessible to students. This affects their motivation for learning, and it makes it much easier. Students find it attractive to draw pictures with the computer, and this is more attractive than proving propositions about numbers. Success in recursion is the result of your action, something that's very easily observed, whereas in induction, it's the validity of your proof, which can be very mysterious. Our goal then in promoting Haskell as a language for mathematics education is to help students and teachers develop the intuitions they need to create proofs and counterexamples. One leg of our strategy for promoting Haskell is to transcode ATM's archived resources from languages like BBC Basic or TI calculator scripts to Haskell. We've assembled some 3,000 pages of text from Micromath magazine, for example, which ATM published for over 20 years. The purpose is not to teach programming, but to learn more about ATM members' philosophy in creating software-supported educational mathematics, and to make these resources available again to teachers. A second leg of our strategy is to promote self-study professional learning materials in Haskell. Teachers who are interested in learning more about this are asked to contact me. And finally, we developed proofs inspired by David's work with Mathematica. Now, at the 2022 conference, Neil and I reported on two archive projects, ATM arms and ATM boards. I'm going to start briefly recapping these, then I'm going to talk about Words into Mathematics, which was an ATM product distributed on playing cards. J. Timotheus developed a TI graphing calculator script for Words in Mathematics, and he wrote it up as an MT article, which we'll link to from the Padlet. ARMS was described in a 10-page booklet, which was distributed with the software, which contained exercises for students from primary school, year 5 upwards. Now, why is this not moving on? The second program, Boards, was a program written by a year 7 student who wrote in Micromath, I've written a program called Boards in BBC Basic. The idea was prompted by a homework problem my maths teacher said. He asked us to find out how many rectangles there are in a 4x4 board. My friend noticed that in a general n by n board, the number of rectangles was the nth triangle number squared. We wondered what triangle numbers have to do with squares and rectangles, so I wrote the program to find out. What you're seeing here is a Haskell visualization of the problem, which can be used to prove, in general, the number of rectangles in an n by n grid is the product of two triangle numbers. We can call them T sub m and T sub n. Okay, the third program is going to be introduced by Neil.
So both the previous examples required schools to install a Haskell development environment on a local computer. They are written using a software system called WorldTurtle, which is a domain-specific language embedded into Haskell, which I wrote. With the next example, we've created it through the web application and ported it as a free development platform, Replit, as an iHaskell notebook. So, in the ATM publication, Words into Mathematics, Geraint Timotheus describes the WIM algorithm. In WIM, a name can be converted into a set of coordinates, which can then be plotted to make a pattern. He had a lot of success in the classroom with this. Using WIM was quite fun for the students. They wanted to plot their own names and see how they came out into the graphs. The algorithm primarily split into 3 parts. First, all the letters are split into consecutive pairs. You can see an example of this in the top screenshot. So, for example, the name Lucy, we've partitioned into L and U and C, C and Y, and finally back to Y and L to close the loop. Next, each letter is converted into a number with some modulus, e.g. for modulus 3, A maps to 1, B maps to 2, C maps to 3, and D would map back to 1. The modulus given by Lucy Cartwright in the same publication is the length of the string plus 1. And finally, to create a rotated pattern, you swap the X and Y columns and subtract the new Y value from the length of the string. This can be repeated multiple times to add additional rotations. So you can see, in fact, in the last screenshot here, that this is applied. And so the first line of the output is the original rotations, the original coordinates, and then each line thereafter is adding a rotation onto it. So in the process of working through these graphs, Timotheus recounts that the classroom discussion moved away from coordinates and transformations towards permutations. Students were now attempting to rearrange words to produce novel graphs and looking at what the different families of graphs were. Many of these mechanical steps can be translated into Haskell as functions. The mechanics of Lucy Cartwright's patterns especially allows us to write functions which can be applied iteratively, and so we can start applying recursion at the higher coordinate level. So in this example, we've taken the algorithm and ported it to the iHaskell notebooks, and also used something called the diagrams package to actually render the algorithm in the notebook itself. In diagrams, we plot the points and we can style and color them as we want. In this next slide here, this is a disciplinary concept graph to cover the key areas that will need to be understood to be able to use diagrams effectively yourself. Now, a sixth former who has worked with Haskell before would perhaps take 30 minutes to work through the initial diagrams tutorials to start being effective. This is something we would expect students who have been on the Glasgow FutureLearn course to be able to achieve. Now, the FutureLearn course is a free self-study course for some part of the year. We have licensed it in trials with Year 12 and Year 13 for their maths and computer science students. And we do have a few free licenses that may be used over the Easter holiday if you're interested in learning more. In terms of the course itself, it's built around 6 weeks of self-study created by Glasgow University. We use the first 3 weeks to cover the basics of Haskell. What is a function? What's a list? How does the Haskell language do expression reduction, and how this contrasts to other programming languages? It also goes further into the building blocks of simple types like Booleans, working with list transformations, and input-output. In the next slide here, a key concept I would like to emphasize is recursion. So in the top left screenshot here, you can have a length function which counts the elements in a list. The first line is the type signature, which describes what the types are that we are working with. We're working with a list of any type producing an integer. The second line is the base case. So for an empty list, return 0. And the final line of the length function is the recursive step, where we add 1 to a running tally while reducing the list down to 0, eventually hitting the middle line and terminating the function. We don't have time to go into details about types and type classes right now, though these are very important. However, we have developed resources for Key Stage 2 that use these ideas, and Ian will describe these.
Okay, so thank you, Neil. We start with the assumption in secondary school that children in primary school will have had exposure by year 6, both to algebra and to the basic computing concepts, which Neil's just mentioned. When they get to year 7, these ideas of algebraic writing and programming should be accessible to them. But not all students will have a sound enough grasp of algebra or of textual programming. So we revert in our training material, both for teachers and students, to Gattegno's approach to early algebra. And you'll recall in that approach, the students given a box of rods to initially sort out and observe 5 things, rods of the same color are the same length, rods of different color are different lengths. The length of any rod is some multiple of the length of the smallest, the white rod, and so on. We add these observations into a framework we call domain or type in Haskell. So we can see in the work with Gattegno's mathematics 3 different domains. The staircase, which is derived from the noticing about the rods, the color palette, which is an unordered set of colors, and the table of complements, which shows a domain that consists of all the rods organized as trains of rods, of 2 rods, equivalent in length to a particular rod. The domain is modeled as a set of color names, a set of colors, and a list which consists, I think, Neil, of a list of lists with 2 colors and a single color. Is that right for the pattern?
That's correct.
Yeah. Okay, so here we can see some code which gives you the generation of the stir case starting with the white rod. So if we go, give me an upstir case starting with the white rod, we get white, red, green, purple, all the way to orange. If we ask for an upstir case starting with the orange, it's the base case, and we get a list back with just the orange. This function call gives this result. This function call gives this result. So the data types are defined using Haskell's object-oriented class mechanism. These are the names of the rods, the color names of the rods. Here we have the equivalent numerical name, if we give a rod a numerical name by measuring it with the white rod. And we can convert between the integer or the numeral to the color, and we convert between the color and the numeral. The palette, the color palette, is represented by a set of mappings from the rod names, the rod color names, to the diagram's color code. You can distinguish the diagram color code name, which has a lowercase initial letter, from the data type for the rod, which has got a capital letter. So here we have a recursive function, SUMC, which calculates what this train equivalent in length, or a rod equivalent in length to a train of a white and a red, is a green. The train equivalent to a red juxtaposed to a green is a yellow. And you can see the base case here is one in which the successor of a rod is returned if it's being combined with a white rod. So the white and the yellow, the successor of would return the successor of the yellow, which is dark green. Or if that doesn't match, it goes on to test the other 2 colors by summing the predecessor of the first with the successor of the second. So it's the predecessor. If you start at the top here with the yellow and the white, the next call on SUMC would be the pink or purple, and the red, the next one would be 2 greens, and so on. We can unfold the program execution in the form that you would represent a proof by saying which equation is operational. So here, SUMC is unfolded. SUMC is unfolded by using this equation. It goes to that equation. You then unfold the inner function calls predecessor and successor, which gives you the white and the red. Then you unfold SUMC again, which is the base case for SUMC, and you end up with the rod equivalent in length of the sum of these 2. Unfolding the equations can be written up very much like a formal proof. Now we're going to look very briefly at a key stage 5 computer algebra project that David Vaccaro has talked about in the past and has been written up in a paper we've published on the Padlet. In this problem, we're asked to prove that if you're given a quadratic equation in which the coefficients are odd, then the roots must be irrational and the discriminant is not a perfect square. David's approach to this is to experiment, first of all, and collect numerical data, make a conjecture based on looking at the data, and then developing a proof of the conjecture. Briefly, I'm going to talk about what he uncovered, and then mention a proof that Greg Gomberg, a mathematician, member of the group, has added to the paper, which shows how by reasoning directly about the parity of the numerators and denominators of the quadratic roots, you can get to this result directly without computer algebra. But first of all, David's approach is to experiment looking at the squares. So here are the squares with the numbers from 1 to 15, and take the residue modulo 8 of the squares. The next step is to do the same exploration with the discriminants. Here's the equation for the discriminant. And there's a bit of code to generate them, and we look at the residues modulo 8 of the discriminants. And then we can see that the discriminants can never be a square number because the residue would have to be one of these. In fact, the residue for odd squares is always 1. The observation that David highlights. And he works through an exercise using GCSE algebra to prove that the residue of the square of odd numbers is always 1. To recap his argument, he claims that the discriminant is always 5 more than a multiple of 8, which means that it must be odd. Because it's odd, it can't be the square of an even number because they're all even. However, it appears that every odd square is 1 more than a multiple of 8, whereas the discriminants all appear to be 5 more than a multiple of 8. And therefore, we can conclude that the discriminant is not an odd number. The final step requires us to observe the rather complicated argument, which we've taken from Wikipedia, that the square root of an integer will either be another integer or irrational. Since we've shown it's not an other integer, it must be irrational. Finally, we have a proof that doesn't rely on computer algebra. In this proof, we speculate that there might be a rational root, which we can write as P over Q in its lowest terms. And we can put P over Q in the original equation, multiply by Q squared, and get this rather elegant equation here. And then we look at the parity, odd or even, of the 3 terms on the left. We know that either P and Q are both odd, or one is even and the other one's odd. They can't both be even because they haven't got a common factor. If they're both odd, then the 3 terms on the left here are all odd, so their sum must be odd. If one is odd and the other one's even, then 2 of the terms will be even and 1 will be odd, so again the sum's odd. The equation's left-hand side therefore always sums to an odd number, and since this can't be 0, our supposed rational root doesn't exist. So to recap, we've looked at several classroom-ready resources. ARMS and boards taken from Micromath at the 2022 conference. Jesse Siegel gave a proof of the fact that the m by n rectangle had the product of the triangle numbers of m and triangle number of n and m, number of rectangles inside it, which is a suitable Key Stage 5 non-examined assessment project. ARMS, we've noted is comes with a 10-page booklet from ATM on how to use the software in Year 5 and subsequently. In Words and Mathematics, we saw how to translate a word into coordinates and draw its image based on a product, an ATM Words and Mathematics gift cards, which was written up by Jay Timotheus as a mathematics teaching article. And in that article, Lucy Cartwright talks about a manual process for how to draw the diagrams. If you go down that route, then the software can be used to check the manual calculation. Finally, we looked at David Vaccaro's use of functional programming in Mathematica to develop a conjecture concerning the roots of a quadratic equation with odd coefficients. And again, we offered a pure mathematical proof which bypasses the need to use the software system. All the people who contributed, and to you for attending this session. And I hope with technology's help, we'll be able to deal with some questions over Zoom in the remaining 10 minutes or so. Thank you for listening.